0 degrees Celsius is the freezing temperature of water. It is the temperature at which water turns to ice. Or is it? The bottle in this video actually contains liquid water and is about -5 degrees Celsius. It can freeze in an instant. You can check this yourself. If you hit the bottle on the counter, you can see it will freeze. You might be surprised to learn that the water in this picture is actually a liquid, not ice. Why doesn't the water freeze? And how can we get it to freeze? Ice freezes because of nucleation. At low temperature, the solid crystalline phase is energetically favorable compared to the liquid phase. An energy barrier has to be overcome, however, which is why freezing does not happen spontaneously. The energy barrier will be caused by a tug of war between the surface tension and the volume energy. Once the liquid has overcome this barrier, nucleation can occur. Nucleation is the process of a phase transition originating from a nucleus. A nucleus can form any time when water molecules come close together. At any temperature, one can define a critical radius. When a nucleus has a radius larger than this, it will grow uninterruptedly, whereas smaller nuclei are not stable due to their high surface energy. The lower the temperature, the smaller the critical radius is. This is why water does spontaneously freeze if the temperature is low enough. This figure shows the temperature dependence of the activation energy. Observe how it decreases as temperature decreases. The activation energy depends on the interface energy, the temperature, and the properties of the fluid. If the energy barrier is much larger than the thermal energy of the water molecule, it is very unlikely for a crystal to overcome this barrier by thermal fluctuations alone. The nucleation chance is proportional to the Boltzmann factor. This means that pure water won't freeze at temperatures below 0 degrees. But normal water freezes way above -48 degrees Celsius. Why is that? The answer is that tap water has impurities in it, like minerals and ions, which can start the nucleation process. When a nucleus forms around a different substance, it's called heterogeneous nucleation. Ice crystals forming on the surface of another material tend to form spherical caps instead of perfect spheres. This reduces the ratio between surface area and volume, reducing the activation energy. The exact reduction in the energy barrier is governed by the contact angle between the ice crystal and the catalyst surface, as can be seen in the topmost figure. The difference between energy barriers can be seen in the lower figure. Thus, the addition of impurities causes water to crystallize more easily, which is why you never encounter supercooled water in the wild. Here we can see how the heterogeneous nucleation has a higher chance of forming a crystal than homogeneous nucleation, especially at low contact angles.
To a Darwinist, it's not surprising that it's so hard to get agreement.
Here is a bottle of supercooled demineralized water. The water is almost completely pure. Therefore, a heterogeneous nucleation will not take place within the liquid. However, what happens when we bang the bottle against a hard surface? A shock wave is sent through the bottle, creating a lot of motion of water molecules. Also, bubbles are formed at the top. This extra motion increases the number of interactions per second, thus the nucleation chance increases. In this clip, we show the working of secondary nucleation. We have a supercooled liquid, and by adding an ice cube, it is extremely easy for the surrounding water to freeze. The ice cube is essentially a nucleus with a radius way higher than the critical radius. Again, we can see that the phase transition extends from this nucleus. To conclude, we have seen that supercooled water needs a nucleus to freeze. This nucleus requires an activation energy to become larger than the critical radius. On a substrate surface, nucleation occurs more easily. For low temperatures, the required critical radius and thus the activation energy is lower, which is why we eventually have ice cubes in our freezer. We can also freeze the liquid by creating a lot of motion and bubbles in the supercooled water. The next time James Bond orders a supercooled beverage, we suggest it neither be shaken nor stirred.